All right, guys, so we're back and we're getting ready to talk more details about calibration curves. And in this video, what I want to talk about is the construction of the curve itself. Now, I know that I told you to run a blank every single time, right, for the machine and kind of include that in your calibration curve. And then we said we need 3 standards minimum, and recommended is going to be 5 standards. And I told you that that number could change depending on who you work for. Sometimes they'll require more, sometimes they'll require less. But don't be surprised if a company will tell you to do 7 or 10 of these, because depending on what they're doing and the method that they're following, it might be needed. But the question always is where do I start? Right? So how low do I go and how high do I need to go? So for instance, if I'm analyzing fluoride content in drinking water, like we've mentioned before, then where do my standards start? How low and how high? Do I just randomly pull these numbers out of midair? And the answer is no. A lot of the times the method that you will be provided with in a laboratory will tell you the concentrations that you need to make. So they will be very specific, and they will say, this is what's required, this is what you need to run. And the reason for this is consistency, right? Someone has made the determination what proper ranges should be present, and then they want you to do those same concentrations every single time for consistency. So someone that made a calibration curve 6 months ago, you can remake those standards today, and you can run those standards today and just replace the data that they made 6 months ago. You don't have to go into the software, you don't have to go into the computer program and change anything as far as the method is concerned, right? So we're just overriding data because you've made the same concentrations over and over. So that is kind of good news for us. It limits what we have to do to think about, right? So we follow a set of instructions, we do what's written on the sheet of paper, we don't question it, we run them, and everything is okay. But what if we have to make the decision ourselves? What if we're doing a new method that requires a set of standards that we've never done before, and your part of your job is to go and help with method development, right? So you're working with a group of people that's all working on the same project, trying to figure out what the best settings are for this method and to analyze these types of samples. So very often, one of those questions is always where, right? Where do I start my calibration standards and where do I end? Well, one of the things that you always have to kind of do first. So the first thing that you have to do is look at your samples. What type of samples are going to be presented? And what is the expected concentration range? Right? Because what you want to do, you want to figure out what the normal type of answer is going to be every time. So when this product is analyzed, or when this sample is analyzed according to this method, what is the average concentration that you're going to see of all of these samples? Because that's where you need to center your calibration curve around. So basically what we're trying to say is that as I analyze the samples, they're going to kind of be clustered. There's going to be a normal window of what we're going to see, right? This cluster of samples needs to be basically in the middle of your calibration curve. So what would happen is that I could do one that's a little low, maybe the second standard that's going to be here, the third standard, the fourth standard, the fifth standard, the sixth standard out here, and the seventh standard up there, if I'm required to do 7. Right? And notice that I put some that are a little bit high and some that are a little bit low, but look how much closer that I've done these standards here in the center. They don't have to be even, meaning it doesn't have to go 10, 20, 30, 40, 50 people, right? Actually, a better calibration curve has more standards around the average area of where you're going to find your samples. That is a better calibration curve, and you will get better data because of that. So have one a little bit low, have one a little bit high, just in case there's outliers in the sample set. but have the majority of your standards around the expected concentrations of the samples that's going to be given to the laboratory. Now, this means that you need to know a little bit about the samples before you do the standards. And this is somewhat normal, right? If we're analyzing an orange juice sample, or if we're analyzing a hamburger bun sample, or if we're analyzing soil that was pulled from Greenfield Lake in downtown Wilmington, we probably have some insight about what to expect or what to find, right? So for instance, if I was looking at drinking water in fluoride, well, what I would do is I would go to the EPA's website, and the EPA says that if it's over 4 parts per million, then this is bad news bears. You need to call the EPA and you need to report it, and they're going to come down and do an investigation. So I probably know good and well that these companies that are in control of my drinking water will not have levels higher than 4 parts per million. So this really gives me an idea of where I should stop the fluoride standards. So maybe this one is my 4 parts per million. I don't need to really go any higher than that. If I do, then we've got bad news that we need to report. And it's just rarely going to happen. All right, well, if I do a little bit of digging, what I would find is that most of the time I'm going to see levels of maybe 0.75 to 1 part per million fluoride in drinking water. It could go a little bit higher, it could go a little bit lower, but on average, this is what I'm going to tend to see. So that basically means that my middle standard here probably needs to be a 1. And then I can do maybe a 0.75 that's here, and then right up above it, I can do maybe a 1.25. And then way down here at the very bottom, I can maybe go to a 0.1, right? And then maybe this one is a 0.3. And maybe this one, it needs to be between 1.25 to 4, so let's say 2.5. I can make the standards anything that I want to make them. But notice that I have clustered at least 3 of these really close together because that's where the majority of my samples are going to be found. This is the proper generation of a calibration curve. It doesn't have to be symmetrical. It doesn't have to be even. It doesn't have to be distributed the same way from standard 1 to standard 5. Not only that, but they don't have to be whole numbers, right? They can be random weird little numbers of 0.1 or 2.5. It doesn't have to be nice rounded numbers like 1, 2, 4, 6, 8, 10, 20, 50. No one said that had to be the case. So this is the whole concept of generating a calibration curve that is proper for your particular method that you're doing in a laboratory. So make sure that you have a span of standards, meaning make sure that you go really low and high, at least on the fringes. But then make sure that the majority of the standards that are important are revolving around your expected concentrations of your samples. And you'll get much better data, you'll look much better as a lab analyst, and that raise might come a little bit quicker for you.